All right. So this is going to be the last live lecture. I will have an overflow lecture, that's for sure at this point. The overflow lecture will be on Brunn's sieves. So those are a little bit more advanced sieves, and they kind of kick-started the modern sieve theory. Now what we're going to do today is we're going to go through the sieve of Eratosthenes more carefully and use it to actually count things rather than just draw a picture and pick out prime numbers in a picture. Also, on Friday, tomorrow, from 6 to 7, I'm going to be in the Blackboard Collaborate room, and I'm going to do a problem session. So you can come if you have questions on homework problems, you can come ask those questions. But if there aren't any questions, I plan to walk through some of the ideas and a couple of the exercises. All right. So yesterday, we started talking about the sieve of Eratosthenes a little bit. And so we filled in a whole bunch of stuff on this slide. We had this intermediate step of the sieve of Eratosthenes. So this is where we had a bunch of integers less than or equal to x, and we had removed the multiples of some of the primes. We had gone through the primes up to z, removed all those, and we stopped at this step. Before finishing that picture we did on the first day, and we're asking, okay, how many numbers do we have left? Is it actually a smaller amount of numbers, like asymptotically? Like, is the proportion noticeably smaller? And so the result we started talking about is kind of the simplest bound you can get on this kind of function. And we talked about, what does this main term look like? Well, it's x times some function of z, which you can show that as z is tending towards infinity, this function is tending towards 0. So if you make z grow a little bit with x, so as the number of possible candidate integers increase, you maybe slowly increase the number of primes that you're eliminating and eliminating their multiples, then this main term will be a lower order of magnitude. But then we talked about this error. The error is exponential in z, which means that z can't grow too fast, because if it did, then this error term would be way too big. Like if we tried to make z equal to the square root of x, and we said, okay, we're eliminating all primes up to the square root of x, and all prime multiples, all multiples of those primes up to the square root of x. Well, big O of 2 to the square root of x is huge. It's way bigger than the number of possible integers we were considering, and that would completely overwhelm the main term. So this is going to be kind of a big theme of these sieves. You're going to get some main term, some error term, and you're going to have to decide, all right, well, how many steps into this sieve can I actually go and still get an error term that's small enough that we can say something non-trivial? And so I put down this example. An example for this theorem that would work is if you picked z equals log x, because then the error term 2 to the log x grows like log x, which is pretty small. And so then the main term would look something like this. So if you eliminate the multiples of all primes below log x, you have asymptotically this many integers remaining that are less than or equal to x. And so we'll talk about a little bit later today what this product sort of looks like, and we'll be able to describe the growth rate of this main term using just differentiable functions. But before we do that, I want to actually prove this theorem and talk a little bit about how we could go about making this error term a little bit better than what we have. So I'll need to insert an extra page that we can actually do this proof. So we're going to prove this theorem. All right. So when we go through this, I'm going to define a few shorthand notations. So we'll call P of z, that's the product of all primes less than z. So these are the primes that we're trying to remove multiples of. Also, if I write a tuple, a comma b, if many of you may be familiar with this shorthand, but I just want to make sure that we're all on the same page. We use this to denote the GCD of a comma b. It just saves a bit of writing and keeps everything short. All right. So let's go through and see where this main term and this error term are coming from. So the definition of this function is that it's the number of integers which are less than or equal to x, so sum over all integers less than or equal to x, such that those integers are not divisible by any primes below z. Well, another way that we could write that is we say the GCD of n with this capital P of z number is equal to 1. That's the same statement as saying n is not divisible by any of those primes. Because the GCD is, well, it's a common divisor between n and this product of primes below z. If it wasn't 1, you would be able to find a prime that divided them both. Okay. So what are we going to do with this? Well, there's a little bit of a trick using the Mobius function that we haven't really looked at yet. And so I want to show you this. This is pretty neat, and it's a very useful technique in analytic number theory. We'll write this as a sum of the divisors of the GCD of n with this product of primes of the Mobius function. So why is this true? Where did this Mobius function come from? Well, this is that property which told us that this is equal to 1 if the thing that we're summing over the divisors of is equal to 1, and it's equal to 0 otherwise. So if this thing we're summing over the divisors of is not equal to 1. So this is really the same sum. It's a sum of 1s in the places we want 1s and 0s in the places that weren't in the original sum. So it's giving us the exact same number. Nothing had to change at all. This is a very useful trick in analytic number theory. It allows you to talk about things like being co-prime or sharing divisors only using the Mobius function. You don't need to use too much about prime numbers themselves, just the Mobius function in order to get at this kind of arithmetic structure. All right, and so now what we're going to do, a pretty nice way to evaluate nested summations is you try to switch the order of the sums and see if that makes it any easier. So I am going to rewrite the inside sum a little bit. D dividing the greatest common divisor of n and this other number, capital P, that's the same thing as D dividing both n and capital P. Okay, now let's switch the order of the sums. So we're going to put the sum over D on the outside. So this is a sum over all possible divisors of P of Z. And then for each one of those divisors, we want to sum over all n, which are less than or equal to x, and which are divisible by D. This should have a D in it, not a Z. And in fact, I can put the mu of D on the outside because it only depends on D and not n. Okay. So that's kind of nice. We now have an inner sum that doesn't involve the Mobius function at all, which in principle means it should be easier to evaluate. And so we can evaluate it by re-indexing the sum. if d divides n, we can write n as m times d. And then n less than or equal to x means the same thing as m less than or equal to x over d. So this inside sum is the same thing as the sum over m less than or equal to x divided by d of 1. The exact same sum. Well, we know what that is. That's the floor function of x over d. Okay, so take a second to absorb how I've rewritten this summation in a way that we could evaluate as a floor function while I add another page to conclude the argument. All right, so I'll go to the next page and I'll rewrite what we have just concluded, which is phi of x comma z is equal to the sum over the possible divisors of this product of primes, mu of d times the floor function of x over d. Okay, well, we've done something like this a couple of times now. We know that we can evaluate this by saying, oh, the floor function is equal to the original thing plus big O of 1. So we end up with something that looks like this. Now I'll distribute the sum to everywhere. The leading term, the x, I can pull out to the outside. And so all that's left is this sum. On the error term, we know that a finite sum of big O's is the same thing as big O of a finite sum of the stuff on the inside, at least with absolute values. So this is bounded above by big O of the sum of d dividing p of z of 1, where right here I'm using that the absolute value of mu of d is less than or equal to 1. Okay. So now we've got some main term and we've got some error term, and these are going to be exactly the main term and the error term that we're looking for. This main term, it's got a factor as a product over the primes that are smaller than z, and the error term here is supposed to be exponential in z. So where that comes from, well, p of z is a product of exactly, well, less than or equal to z primes. Maybe not exactly. Product of less than or equal to z primes. It might be significantly less. It's technically pi of z primes, but for this error, we're just going to say less than or equal to z primes. Well, a divisor is a product of some subset of those primes. So d dividing p of z implies that d is a product over some subset of the set of primes less than z. So this sum, this is the same thing as counting the number of subsets of the set of primes smaller than z. Well, there are less than or equal to z primes smaller than z, and if you have a set of size z, or smaller, then the number of subsets is exactly 2 to the z. The number of subsets of a set of size z is 2 to the z. And that's where that big error term comes from. We're counting all the possible divisors. So it's basically saying all the possible collections of primes smaller than z that could divide an integer m. Okay, so that's the error term. That's where we get the plus big O of 2 to the z. So the main term, for the main term, we look at this sum, and this is supposed to factor somehow. Well, we've got kind of the same idea going on here. It's a sum over divisors of p of z. So we can write this, still got the x, and do it as a sum over the possible subsets of the primes. Well, we'll start with the smallest one, the empty subset. If d is divisible by none of the primes, then d has to be 1. So the first term is mu of 1 divided by 1. That's just a 1. Next, we look at subsets of size 1. Those are specifically primes that divide p of z. And if we plug in a prime, well, mu of a prime is negative 1, so this is going to be a minus, and then 1 over p. The next kind of subset are products of 2 primes. So we get p1 and p2, which are distinct primes, dividing p of z. The Mobius function of a product of 2 distinct primes is positive 1, and then you get 1 over p1, p2, minus dot, dot, dot. This pattern continues for all the possible sizes of this subset. Now, when we've written it out like this really is the multiplied out version of, maybe I'll write an intermediate step, x of 1 minus 1 over p1, 1 minus 1 over p2, 1 minus 1 over p3, etc. Because when you look at this product, for every single term, you pick either a 1 or a minus 1 over p. If you pick all 1s from this product, that's the one on the far left. If you pick all 1s except for a single minus 1 over p, that's one of the entries in this sum. If you pick all 1s except for 2 minus 1 over p's, so maybe minus 1 over p1, minus 1 over p2, that'll give you an entry in this sum, and the minus signs cancel out to make this positive, and etc. And so if we write it using this capital pi for product, we end up with this main term that the theorem told us we should get for the size of this function. Okay. Now, what we're going to do next, before we start talking about how big this main term is, before we talk about the main term too much, let's talk about the error term. We're going to discuss an idea due to Rankins that can improve this error term pretty significantly. So the idea has to do with the sum over d right here. This piece and this piece. So when we did this whole process, we said, okay, we're summing over all possible values of d. And in our error, there's 2 to the z possible values of d. That's why our error term is so big. If we wanted to improve the error term, one of the things we could do is say, well, maybe not all the d values are important. And in fact, that's true. We know we've got this floor function here. Technically speaking, that floor function is only non-zero for d less than or equal to x. So that tells us that this error term really shouldn't be bigger than x, because we shouldn't be summing over any more than x divisors d, because those are the only candidates that could make a non-zero term of this floor function sum. And so if we include this extra condition, d less than or equal to x, we might be able to improve the error term a little bit. Now, we can't just say, oh, throw in a d less than or equal to x right here and say, oh, this is smaller than x. Big O of x is too big to say anything. We already knew that we were pulling integers from the set of all integers less than or equal to x, so we already knew that everything was less than or equal to x. So if we add this condition, d less than or equal to x right here, and right here, we'll need to actually be able to give a stronger bound on this sum than x. All right. So that's the idea of where we're going. So this is where we define something called a z-smooth number. That's what we've got on the next slide here. We use a different Greek letter, psi, and we say this is all the integers less than or equal to x, such that any prime dividing an integer has to be smaller than z. So this condition is saying that n is a z-smooth number. It's only divisible by primes less than or equal to z. And so what this tells us from the last slide if we take the spot where we started on the last slide, and we instead notice, well, hey, this floor function is only non-zero if d is less than or equal to x. And we include that extra condition. Oops. Then when we multiply everything out, we get x times this sum plus big O, and now it's the sum over d less than or equal to x and d dividing p of z. And so in particular, d is a z-smooth number. It divides a product of primes less than or equal to z, so it must be square free and only divisible by primes less than or equal to z. So we could write that error term is at most the size of this set of z-smooth numbers less than or equal to x. This is a bit of a different expression, and the hope is that we could show that this error term is a little bit better than exponential in z. And in fact, we can. So there's two things that we have to do in order to make this approach to improving the error work. We actually need to bound this. That's the one thing we have to do, which is the goal of what we're doing. But then the other thing, we need to make sure that in the main term, this doesn't break anything. So we'll call this 2. That's sort of the two-step process to checking to make sure that adding this extra condition really does give us a stronger result. All right. So first thing we'll do is we'll bound the error term. So that's what we've got on this next slide. The number of z-smooth integers, which are below x, is at most this big. So compare this to 2 to the z. At least in terms of z, this new error is much smaller in terms of z, right? This new error, log z, is very small in z. It grows very slowly. And then in the exponential function, well, that's even smaller. Log z is on the denominator. You have a negative in the exponential function. This exponential here is always going to be smaller than 1. So at least in terms of just z, this bound is leagues better. Possible confounding factor, though, is that this new bound involves x's in it. So we actually have to be a little bit careful. The parts with z grow much, much slower now, if they grow at all. But because there's this x out front, this error term is really only significant if this whole thing grows slower than x. Because remember, we're counting this belongs to, this thing is, I'll write this in blue. This is contained in the set of integers less than or equal to x. Or, well, maybe I should put a size here. Say it's bounded above by this. So the trivial bound is big O of x. In order for this theorem to actually be significant, we need to pick z in such a way that all this stuff ends up growing slower than x. All right, and I'll show you an example of that later. I'll wait until after we get the improved statement for phi, because for phi you'll get a similar looking error term to this. And then I'll say what is a nice value of z that we can plug in. Okay. Here's where we use Rankins trick. This psi function is the sum over n less than or equal to x, such that n divides this capital P function, so these are C smooth numbers. And then we're going to say, well, let's actually bound this above by something that looks like this, where delta is something bigger than 0. This is Rankins trick, and the reason for this sort of trick is that now when we have it written out like this, there's sort of an Euler product factorization that works out quite a bit nicer. Having larger values for delta here gives us products over primes that are easier to evaluate. So the x to the delta can be pulled to the outside. What's left over is a sum of 1 over n to the delta, n less than or equal to x, n dividing this product of primes. This is pretty much the same setup that we had earlier with the Mobius function divided by d, and we said, hey, that's secretly factored as a product of primes. This does the same thing. This factors, so we have x to the delta times the product over p less than z of 1 minus p to the delta. I think I have a typo on my slide here. Yeah, I don't want this condition. Hold on 1 second. I'm going to fix that. We want this. Okay. So real quick, why did I have to fix that? Oh, and actually Owen asked a question just now that hits right at this point. A z-smooth number doesn't have to be square-free. That's sort of the part that I was missing. That product of primes, capital P, is just a product of one copy of each prime. But you still get a z-smooth number if one of those primes shows up more than once. 32 is still a 2-smooth number because it's only divisible by the prime 2. But 32 definitely does not divide the product of all primes less than or equal to 2. So really we want this condition instead. All right. So let's factor this product again. We've kind of got the same situation going on. For every single one of these terms, 1 over n to the delta, we pick what power does the prime divide n to the delta? Well, it might not. So you might have to multiply by 1 for that prime. It might divide it once. It might divide it twice. It might divide it 3 times, etc. Inside this product, that's a geometric series. And if you've worked with zeta functions at all before now, you'll probably recognize what's going on here. The geometric series converges to this quantity. All right. Let me add 2 more pages. So now we're once again coming up to this product over primes less than z of something involving those primes. And we once again are looking for some way to think about this bound. So I'll show you a nice trick here that you can get a pretty sharp looking upper bound. And then a little bit later, I'll mention the main result that tells you how fast this type of product grows. So this function is bounded above by x to the delta, product of p less than z of this product. Now, I really don't want the inverse on top, so I'm actually going to factor this. As this product. This is really just a difference of squares. This is 1 minus the thing squared. And so when you do difference of squares, one of the factors is this one of the factors is this one. So if I multiply by this, it will cancel out. All right. And so why would I do that? Well, I'm going to write these two products separately. This converges as z tends to infinity. The way that you would prove something like this is you would multiply it all back out, and you could bound it above by a p series where p is equal to 2. So that's just bounded above by some constant. Yes, Alvaro.
Yeah, there is a question. Is it an inequality between the sum to the product of geometric series?
Back here, from this sum to the product of geometric series, no. This is actually an equality. This really is equal. Because every single one of these integers n is written in a unique way as products of powers of primes which are smaller than z. So every single one of these terms comes from a unique term in the expansion of this product. Vice versa, every term in the expansion of this product is 1 divided by a product of powers of primes smaller than z to the power of delta. So that's automatically one of these terms in this sum. You have to worry a little bit, just a little bit, about convergence properties. But because these are geometric series that automatically converge, the convergence is not really going to screw up this expression at all. And more than the fact that these geometric series converge, they converge absolutely. Okay. So back over here, I should technically say that this product converges if delta is bigger than 1/2. So that we can get a p series that's actually convergent.
Sorry, there was a follow-up there.
Okay.
The follow-up was, but one sum is finite and the other one is not?
But one sum is finite and the other one is not. Oh yeah, because I still have the less than or equal to x. You are absolutely right. I should be erasing that and putting a less than or equal to right there. Yes. You're absolutely right. Thank you for pointing that out. I am really bounding above by an infinite sum, which is still convergent because it converges to this product of geometric series. That's a good catch. All right. Let's go back over here. This sum, as long as we choose delta to be large enough, this is going to be convergent. So we can basically get rid of that. That's going to be bounded above by a constant. So up to a constant multiple, we get an upper bound that looks like this. All right, now here's the trick. Write this in blue. 1 plus x is less than or equal to e to the x. This is an inequality that you can prove using calculus techniques. You can compare the Taylor series of e to the x with 1 plus x, or you can just look for an intersection point and check derivatives, things like that. So using that relationship, this is bounded above by the product of the exponential of 1 over p to the delta. Products of exponential functions obey very nice rules. This is bounded above by x to the delta times the exponential of the sum of p less than z of 1 over p to the delta. All right. And so what will we do with this? We're going to define a few things. We'll say delta is 1 minus eta, or eta small, to ensure that delta is bigger than 1/2. This way, p to the negative delta can be written as p inverse e to the eta log p. And then we'll also use the fact that, and I'll write this in blue because it's a fact, e to the x is less than or equal to 1 plus x e to the x, which is what we'll use to bound that quantity. So putting these together in order to bound the sum inside the exponential function, we'll get a bound that looks like x to the delta exponential of sum over p less than z p inverse 1 plus this exponent times e to the eta log p. Now we just have to pick some value of eta which is sufficiently small. So we choose eta is 1 over log z. In fact, I forgot to plug in right here. Delta is 1 minus eta. This is x to the 1 minus 1 over log z times the exponential sum over p less than z 1 over p 1 plus log p over log z. And now this expression, this is e to the log p over log z, which is less than or equal to p to the 1 over log z, which we know is less than or equal to z to the 1 over log z, which that is actually equal to just e. It's a constant. So I can throw a constant right there. All right, and then what's left? When we multiply everything out, we have a term x to the 1. We have a term x to the negative 1 over log z, which is the exponential of negative log x over log z. And then we have this big exponential term, but when we multiply everything out, that's the exponential of sum over p less than z 1 over p plus e over log z times the sum over p less than z of log p over p. And both of these sums are sums that we looked at yesterday. This is log z plus big O of 1. This one will get e over log z times log z plus big O of 1. And there's a whole bunch of cancellation. E over log z times log z, that's just e, it's a constant. E over log z times big O of 1 is smaller than a constant. So really, this is big O of 1. This is big O of 1. This is big O of 1. E exponential of big O of 1 is a constant, so the only term left here is exponential of log z. But exponential of log z cancels out and just gives you a log z, which is the term that we expected from the original statement of the theorem. All right. So this is a little bit of a lengthy process, and Rankins' trick is it's by no means something that's trivial to come up with. And the fact, we picked eta and we picked delta, this is something that comes through with a lot of practice and things saying that, oh, well, we want delta to be smaller than 1 because that's this power of x. We want it to be smaller than 1 or maybe 1, but we don't want it to be too small. And in fact, we can get the best result when it's smaller than 1, but only just barely. So we say it's 1 minus some function that's tending to 0. So this is where we get the improvement in the error. This is smaller than 1, but only just barely.
One comment, Brandon.
Yeah.
There is a comment that says, does eta 1 over log z give the optimal result? How do you know how to choose it?
That's a good question. Eta equals 1 over log z. I actually don't think that gives the optimal result. I'm not sure if it's optimal or not. How do you know how to choose it? Well, the idea is you want to make sure that eta is something tending to 0 as z tends to infinity. But then the way that you choose it is by choosing something that is easy enough to work with in the other terms in this upper bound. So 1 over log z was really nice because this e to the eta log p was just bounded above by a constant. And that was super nice. So that's one way that you can say that you've made a good choice. It's something that tends to 0, and it's something that greatly simplifies all this extra stuff. But sometimes it can be hard to decide if you've got the optimal choice or not. You could have picked some other function for eta that tends to 0, plugged it into all this stuff, and still ended up with a non-trivial upper bound here. All right. That's where we get this bound for the error term. How do we do the main term? So I'll back up a few slides to remind you of what we're going to do next. We just bounded this piece. And now we have to take care of the main term piece. We have to make sure that writing d less than or equal to x in this spot doesn't screw anything up. And so the way that we do something like that is by obel summation. So let's go forward. We'll remember the upper bound for c is x log z times this exponential. And then we'll be able to prove this result for phi. We got the same main term as earlier, and our error term, it's only a little bit worse than c, but possibly a lot better than 2 to the z, that original exponential error term that we had before. All right, and so where does this come from? We had this expression from earlier, where we already proved that this thing is bounded above by this. And so that certainly falls into the error term. Squaring the log z could only make this bigger. So our error term is smaller than this. All we have to do is now consider this main term piece and actually show that this asymptotically agrees with our original main term. So we take this expression, and let's just say we're very hopeful, and we'll say, all right, well, we'll pretend it's equal to the original term, which is the product of p less than z, 1 minus 1 over p, and then subtract off the terms that are too big, where d is too big. We're going to bound this piece using Abel summation. So the absolute value of the sum over d bigger than x of d divides p of z, u of d over d. Well, in absolute values, we'll just get rid of the absolute value. So we got a 1 over d right here. So Abel summation says this should look like integration by parts. Let's pick out a few things. We'll say our sequence is 1. I'm going to use d actually. If d divides p of z and 0 otherwise. So that a of t is the sum over d dividing p of z, d less than or equal to t of 1, which is bounded above by this c function we had earlier. And then what's left over is our choice of function. F of t is 1 over t. F prime of t is negative 1 over t squared. So we plug in all this information, including the upper bound for capital A. We get a times f from x to infinity, because this bound, the sum is between x and infinity, so we'll need to take a limit of an improper integral, minus the integral from x to infinity, upper bound for a times f prime of t, which cancels out the minus sign so that we can still actually use the upper bound for a, like this. And we get an expression that looks like this for this little error piece. And as long as we can show that this expression is no bigger than this expression right here, then we'll be okay. And the proof that this thing in the green box is no bigger than what I've put in this big O is really just take the upper bound we had for C, plug it in these two spots, and evaluate. It turns out when you plug in this upper bound for C, the integral will turn into some constant in terms of z times a power of t, which you can integrate with the power rule. It's not too tricky of an integral. And when all is said and done, these two things put together will be no bigger than this expression. So I'm starting to run out of time a little bit. So I'm not going to walk through the process of actually plugging in the upper bound for c and doing the integral and everything. I'll leave that for you to work out. What I would still like to do is talk about how we know how big this main term is. So we'll put a little box here to say that I'm going to stop this proof. So this main term, how do we know how big this thing is? Well, on the next slide, we've got something called Mertens Theorem here, which Mertens actually figured out how big this is. It grows like 1 over, well, it not grows, it decreases, it tends to 0. Like 1 over log z times a special constant, where this special constant gamma actually shows up in one of your homework problems. This is not an easy proof. Some of the best ways to prove it involve complex analysis to relate gamma to the Riemann zeta function. But you can sort of get part way there using that exponential trick that we used earlier. This is less than or equal to the product of the exponential function of negative 1 over p, or p less than z, because 1 plus x is less than or equal to e to the x. So you can move the product inside the exponential as a sum. In fact, I can move the minus sign to the outside of the sum. We know what the sum of 1 over p does. This is the exponential of negative log z plus big O of 1 Exponential of big O of 1, that's bounded above by some constant. Exponential of negative log z, we can move the minus sign inside the first log. And we'll get, this is big O of 1 over log z. So we sort of get a sense of how big this thing is. If z is growing with x, we can say, oh, this will give us a sense of how quickly this term is tending to 0. So how much does this main term improve on x? Well, it improves on it by about log z. So depending on what you pick for z, that will give you your improvement. And so the last thing that I want to end with, I want to tell you a particularly useful choice for z. We'll pick z is this function. Oh, sorry, that's not right. I want log z is that function. So z is the exponential of log x divided by some constant a times log x. So why would we pick this choice of function? Well, the main term, remember, this product grows no faster than 1 over log z. So this is smaller than some constant a times x times log x divided by log x. So that grows a little bit slower than x. The error term, big O of x log z exponential of negative log x divided by log z. If we plug into this function, what's going to happen? We plug in z to this function, we'll have, I'll just write less than. Oh, this should be squared. We'll have x log x squared divided by a log x, still squared. And in the exponential function, log z is log x divided by a times log x. So the log x's will cancel out. And this is negative a log x inside the exponential. So what's so useful about this? This is the same thing as log of log x to the negative a. So when you cancel out with the exponential function, this exponential term looks like 1 over log x to a possibly large power. And so plugging all that in, you end up with the upper bound. We'll put an x on the numerator. A log x to the a is coming from this exponential function, minus 2, because we've got this 2 in the numerator, or in the exponent here, log x squared in the numerator, and then times log x squared. And as long as you picked a to be big enough, this error term will be smaller than this main term, because this denominator, you can make the denominator grow faster by choosing a to be larger. This is a very useful choice of log z, and I'll mention it again in the overflow lecture, which will be posted sometime this weekend. All right. So that's where I'm going to stop for today. We talked about the sieve of Eratosthenes. We talked about what does the main term look like, what does the error term look like, and what's a strategic choice of z that actually gives you some non-trivial result. The remainder of this section in the slides, if you go through and look at the slides, this is working through the sieve of Eratosthenes in a bit more generality to get this really big result here. I'll talk about this a little bit in the overflow lecture before we jump into Brunn's sieves, but we just don't have time to talk about that today. In your homework assignment in this section, there's a problem that asks you to use the methods of the sieve of Eratosthenes in order to prove that there are infinitely many twin cube-free numbers. So two cube-free numbers that differ by 2. You can prove that with a sieve of Eratosthenes, and one of the problems in the homework walk through that in the step-by-step process. So I highly recommend thinking about that problem at least a little bit.